Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's class, we will discuss on the velocity triangles, work done, and efficiency in case of Francis turbine. That we will take it up. So the velocity triangles already when we dealt the impact of jets, there we have already discussed the same. From there I will take it. And the uniqueness in the case of Francis turbine is the discharge is radial at the outlet. That is the one important point that should be there in your mind. The discharge is radial at the outlet. The discharge is radial at outlet. If that you remember, accordingly, we can really write the equation for the basically work done after preparing the velocity triangles. Then once work done is obtained, the whatever the efficiencies of the turbine, which we know whether it is hydraulic efficiency, the mechanical efficiency, or overall efficiency, those things we take up for exclusively Francis turbine. So, in this lecture, we are discussing regarding the velocity triangles, work done, efficiency in case of Francis turbine. First thing is the Francis turbine. If I say, you all should understand that it is an inward radial flow reaction turbine with radial discharge at outlet. This is the important. Already the velocity triangles which we have discussed previously, so this is the absolute velocity, and this will be basically the velocity of the wheel, and then naturally this is the relative velocity, and this is called as the inlet velocity triangle, IVT. Right now, if you take the components of V1 in the horizontal direction and vertical direction, then we call this as the horizontal component is called velocity of will, and the vertical component is called as velocity of flow. Then the angle made by absolute velocity with the horizontal is called as alpha. The angle made by the relative velocity with horizontal is called as theta. Theta is called as vane angle. Alpha is called as jet angle. This is what the inlet velocity triangles, which already we have learned. Now coming to the outlet velocity triangle. So the outlet is, first thing is VR1 comes out like this, and then actually this is U2, and then actually if I join this, this will be V1. So this is outlet velocity triangle, right? Over. Then if you take the components of V1, sorry, V2 in the horizontal and vertical direction, this is VW2, this is VF2. Then if I take the angle made by relative velocity with the horizontal at outlet is called as phi, whereas the angle made by absolute velocity with the horizontal at outlet is called as beta. This is the thing that which we have learned. Now, when I say if the discharge is radial at outlet, if the discharge is radial at outlet, that means beta is equal to 90 degrees. So when beta is equal to 90 degrees, the outlet velocity triangle changes like this. So this is VR2, this is U2, and this is V2, and this angle is phi, and this angle beta is equal to 90 degrees. So in such a case, V2 is nothing but VF2 and VW2 is equal to 0. So this is exclusively for Francis turbine. This is general, this is Francis turbine. And already we know, basically, we have studied the equation for the work done. The equation for the work done per second is equal to, we have studied it as rho A V1 into, right? VW1 U1 plus or minus VW2 U2. This is what the work done that which we have studied already. So in this AV1, I call it as we rho Q into VW1 U1 plus or minus VW2 U2. In this, VW1 is the velocity of whirl at inlet, U1 is the vane velocity at inlet, and VW2 is velocity of whirl at outlet, U2 is the vane velocity at outlet. So if I take it, so what is VW1? VW2 are nothing but actually the velocities of whirl at inlet and outlet. Right? Anyhow, U1 is equal to, basically we call it as the tangential velocity of wheel at inlet, and U2 is same at outlet. So if I write what is U1 is equal to pi into D1 into N by 60, where D1 is equal to dia of, basically, the runner. Which dia actually? It is outer dia, because water enters at the outer periphery. N is the speed of the wheel in RPM, and U2 is equal to pi into D2 into N by 60, where D2 is equal to the inner dia of runner, right? So therefore, if I start writing, so work done per second per unit weight of water is equal to rho Q into VW1 U1 plus or minus VW2 U2 divided by rho Q. Rho Q is mass into acceleration due to gravity. This will go. So it is VW1 U1 plus or minus VW2 U2 by G. For Francis turbine, as the discharge is radial, at outlet, beta is equal to 90 degrees, VW2 is equal to 0. Therefore, work done per second per unit weight of water is equal to VW1 U1 by G as VW2 is equal to 0. So this is the final thing, right? Then let us go into the efficiencies. Efficiencies. First one is hydraulic efficiency is equal to, this is power developed by the runner, power developed by runner by power supplied to run. So this is water horsepower. So therefore it is equal to VW1 U1 plus or minus VW2 U2 by G by power support. Water horsepower is gamma Q into H. So per unit weight, if I take it, because the numerator is per unit weight, so also denominator also should be per unit weight. So that's why it is H. Therefore, eta H is equal to VW1 U1 plus or minus VW2 U2 by GH. This is the important thing. So, right? Or otherwise, for Francis turbine, for Francis turbine, as beta is equal to 90 and VW2 is equal to 0, eta hydraulic is equal, hydraulic efficiency is equal to VW1 U1 by GH. Very, very, very important. Then coming to the next, what is basically the overall efficiency? The overall efficiency is equal to hydraulic efficiency into mechanical efficiency. That's all basically. And overall horsepower, overall efficiency is equal to shaft horsepower divided by water horsepower. So here I stop this lecture and we will take up the next topic, which I call it as the working proportions and of the Francis turbine and also the design of Francis turbine in the next class.
Like, share, and subscribe. Hit the bell icon for more updates.